All right, guys, let's get started. So we're currently on week 3 now. So believe it or not, we're already into week 3. Right, so today is Tuesday. We're going to do lecture. We're going to continue with our topics. Today, one of the main topics will be integrity. Right, so before we've been covering confidentiality, and that's when we want to scramble the data so we can't really tell what's being written or what's the secret. Here, it's not about confidentiality, it's just about integrity. So we want to make sure that the data has not been tampered with, but we can read it. You see that? So it's a different kind of a pillar. So we're going to take a look at that. There's several ideas that I'll cover today. Stream ciphers probably also will be covered. Okay. And then we're gonna, these ideas lead us into some algorithms. So very soon, I'll be covering the XOR algorithm in Python. So we've had that first exercise where you did the substitution cipher in Python. And so now we're gonna start doing that. So let's begin with the the course website on Brightspace. Let's take a look at kind of what we've covered. So we've covered the secret key encryption, the substitution cipher. So I've assigned this, right? You can see it's available. It's due September 11th. Okay, so in a couple of days. And we went over this in class, right? So we discussed it. And that was really just a warm-up. It's kind of, your first Python example, kind of getting into the idea of how the algorithms usually work. You'll see the XOR is similar, but obviously now we're going to be introducing the XOR operation. And actually that's really important because then we can build a hash algorithm using XOR. We can use XOR for CBC, for ECB. We can use XOR for the data encryption standard, and so on. Right, so it's a fundamental operation leading up all the way to AES, right? AES is an algorithm that is so advanced that I usually leave that one if you want to do that for your term project, for instance, at the end of the semester. You could implement AES. Okay, so that's the idea. So we've covered secret key and substitution, and you can see here we're kind of in these two modules now, hash functions. So there's going to be a lab, obviously, on Thursday where I'll do, it's an easy one where we will do a few, using OpenSSL, how to calculate some hash values, and I'll motivate some of those ideas. There's some slides as usual. There will be some notes on the README on the repo on GitHub, so you can also read through those materials later as you'd like. But it's what I'm discussing today. And then we're going to have a set of problems related to OpenSSL. Right? And that's more OpenSSL, so it's command line on the terminal with your virtual machines. And then there's this nice little thing, which is to implement an algorithm using XOR. Right? So I usually move these around, so one might go first, the other one goes second. It just depends on how the class progresses, but this is kind of the target for this week. Right? So for those of you that like to start working on your labs, you can go ahead and give it a shot. Right? And I'll cover this in class, of course, later. But yeah, so these two modules, once so this is just a warm-up with XOR, introducing XOR. And then, of course, we're going to build on that, going back to symmetric encryption, and as you can see, the data encryption standard. So this will be, in the coming weeks, week 4, and so on. All right, but today we're going to do some lecture topics. So talking about hash functions and some of those ideas so that we have a proper definition of this. So I'm going to go ahead and switch over to the whiteboard. New whiteboard. Okay. Now, as I said, these notes are on Brightspace, and I'll also provide additional versions of this on the README on GitHub. All right, so the topic that we're talking about, so this is kind of like hash, right? So hash values, everything involving that. And it's very interesting, right? So this is a really, these are very interesting things. So for those of you that, you want to look at this, why is this important? Well, it's important because every time you download software off the internet, you want to make sure that it doesn't have a computer virus. And guess what? The way that you check for that is by having a hash value of it, right? So you have a value, and that's what we're learning, right? The power of these things. Remember that, you know, these we don't rely on these because of security through obscurity. In fact, we know everything about the algorithm, and we just trust that the algorithm works really well because they have been tested many, many times. Okay. So yeah, hashes are used for for securing software, and also, nowadays, blockchain, Bitcoin, your favorite coin, Ethereum, whatever it is, all of it is, based, basically on hash values. So we'll see this. This is kind of one of the last topics at the end of the semester, but obviously a big thing that's going on right now in the world, right? So these cryptocurrencies are electronic currencies, but they are in fact all based on this principle of the hash function and how it works. All right, and so today we're going to see a simple algorithm of how to implement one efficiently. But before that, we want to see some definitions. Okay, so this falls under the title or topic of message integrity. So this is going to be message integrity, and this is the pillar. So integrity. Okay. So this is you want to make sure that when you send a message, you say something like buy the stock at 100 per share, right? You're going to send something along with this. Let's call it a tag. And people are going to check that tag, right? So if you receive a message that has been modified in transit and says buy the stock at 200 per share, then when the people receive this message, they'll calculate a new tag, call it tag hat, and when they compare these two tags, they're going to be different. Do you see that? So that's essentially the principle of what we're doing with integrity, right? So you have this check to make sure but notice that I intentionally sent the message in plain text. So this, the integrity just relates to the data not being changed, but, it has nothing to do really with confidentiality, right? So the message is if we wanted to have confidentiality and integrity, then yes, we would have to encrypt this and also hash it. Do you see that? So we have to do those steps. All right, so that's essentially what we're doing. So we want to make sure that the files have not been changed, which is what I just said. The basic approach is to provide what is called a message authentication code. So this is another term that you'll see in the notes, the MAC, and it's a message authentication code. Authentication. All right. So let's look at the diagram of how this would work. Remember, there's going to be some functions involved here. I'm going to use Bob and Alice again. So we have Alice. So we have Alice, right? And then we also have Bob. Okay. And they're trying to communicate. This time, they just want to make sure that the message has integrity. So we're going to assume, once again, there's an algorithm that's deterministic, but the algorithm takes in a key that is random, right? Or, as random as possible, right? Let's call it secure, has random security. All right. All right. So now what's going to happen is Alice sends to Bob a message M, message, which we usually call M. Remember, this is just plain text, but we are sending alongside of it a tag. So this is the tag. Okay. And this can be something like, essentially, remember, we're talking about bits here in byte arrays. So this is 100 bits, essentially, right? Which is, this week, we're basically going to see how to take anything in Python and convert it into a byte array. All right. So that's essentially how this works. So Alice will use something called a max signing algorithm, which we're going to denote as S, for instance. So this is the signing. So signing is a term that you will see a lot this semester as we talk about certificate authorities. And, these are even more complex concepts, right? So in a certificate authority, we're going to start using like everything. We're going to use integrity. We're going to use confidentiality, authentication, public and private key encryption. So that's a very complex, set of techniques, right? So, it's kind of like somebody understood this cryptography stuff really early on when the internet started, right? Understood everything that was happening. And then they're just like, oh, wow, I can create a company out of all of this. And they created companies like VeriSign and so on, right? So just to make sure that there was integrity and security in the internet. And all they do is run algorithms. So, but we're going to see, so this is one of the basic building blocks, like the second, right? So we have our signing algorithm. Let's call it signing algorithm. So this is just going to be pretty simple. The function S, the signing algorithm, is going to take in the key and the message, and it's going to produce this term we've been using called the tag. Okay, so we're going to use, create this tag. We need to kind of define this, but notice there's going to be some patterns here. So the message, something big, could be pretty big. What if it's like all of the Linux code, right? The firmware for Linux or something like that, right? So it could be pretty big. And then the tag, obviously, we don't want it to be that big because, that we would be sending so much data, right? So think about that. There's already this, goal of having a lot of data be converted into a small tag. All right, so then Bob on the other end is going to, so Bob here will use this something called a verification algorithm. So Bob uses is a verification algorithm. And right now, the algorithms, as I said, we don't worry about them. We just treat these things as functions. But you can already see that a lot of these things are going to be based on the XOR operation, as we will elaborate. So the verification algorithm, we can call it, the function V. So now to verify, so I'm just going to say here, to verify, we will denote this as V, the function that takes in key K, takes in M, the plain text message, because we don't need confidentiality here, right? Later, if you need to have confidentiality, then this would be replaced with C. And then this is, of course, the tag. And this algorithm, all it produces is a yes or a no. Or true or false if you want to do that. And that's essentially what's happening. So you have a verification algorithm. You download your software, you run the function. We'll see this in OpenSSL, etc. And boom, it just says, yeah, it verifies. So if it verifies, good. You can continue. If it doesn't verify, you got a problem, right? So that's the idea. So implementation, and I'm sure you guys have heard of hash values in programming, actually. So I'll make a note of, where you heard about that. But, it's a very nice technique, very useful, obviously, because not just for integrity, but for Bitcoin and all that. So The implementation, MAC algorithm. So now we're kind of talking a little bit about the MAC algorithm, which would be like the signing algorithm or the function. So MAC algorithms can be constructed from other cryptographic primitives, such as cryptographic hash functions, block cipher algorithms, etc. Right? So we are using the same building blocks. Okay. So here is probably the most important thing about hashes. And I can just state it in like one sentence, but it's very important. I can tell you this is usually an exam type question I like to ask. All right, so make a note of that. And it's very simple, right? So what is a hash function? Okay. So what is the definition? Because we don't have to, dive into the algorithm as you can have many algorithms, right? You could have quantum hashing algorithms, right? Why not? But the goal is that that the idea is that it meets the goal that you want. Okay? So let's just say here, what is a hash function? What is a hash function? Okay. All right. So we're going to define a hash function is an algorithm. So a hash function is an algorithm and this is the key that maps data of variable length, data of variable length to data of fixed length. And that's it. So essentially, we have something pretty big. We run it through a function, and that function will map it to something of fixed length, but that is very unique, right? So even if let's say it's a movie, like that movie, Formula One, 3 hour movie on Netflix or something like that. So that movie, I could run it through a hash algorithm, let's say, and it's variable length, right? Really big. But always that algorithm will produce just a sequence of 256 bits, for instance, fixed length, regardless. Okay. And the key thing is if I go in that movie and just change one bit, and I'm talking about just one bit of the whole 3 hour long movie, guess what happens to that hash value? It changes completely. Do you see that? Do you see how important that is? So that's essentially what we're trying to build. That's why Bitcoin is so secure, right? So that's why blockchain works, right? Think about something that big. You run it through a function, it produces a hash value. Even if you just change one bit of it, completely different values. So then the integrity of it has been affected. That is really important, right? Some people, have thumb drives with Bitcoin or something like that, right? So it'd be pretty terrible if you could somehow duplicate that, right? So this is fundamental for that. Do you guys see that? Does that make sense, guys? Any questions? So of course, there's going to be multiple algorithms that we're going to use to make this change, but this is the definition of it, the goal, whether you're using, XOR or anything more advanced. So yeah, so hash functions are primarily used to generate a fixed length output. So that's, key. So you can think of this as 256. You guys have heard of MD5, I'm sure, and SHA-256, right? So that's what that implies is that, what you get out is something fixed. So So essentially, hash functions in programming, also, for instance, Python, the Python dictionary, I don't know if you guys know this, but the Python dictionary, which you may have used, is actually a hash table, right? And so the Python dictionary is very efficient, right, for data structures, etc., because it is ultimately a hash table. And what is a hash table? It's simply a mapping of data to codes, right? So that you can look up the code more easily than the data. All right, so hash functions are primarily used to generate fixed length output data that acts as a shortened reference to the original data. And this is useful when the data is too cumbersome to use in its entirety. Maybe images are too big, etc. So it just makes more sense to just have the hash version of it and then process and then retrieve the actual data later. But that's just an aside of what a hash table is, okay, in a data structure context. All right, so that's it. That's the definition, right? So you just learned that this is used for integrity. You just learned the goal of a hash function. We've discussed that it can be used for many things, as we will see later on. But now, I haven't really said anything about the algorithm, right? The underlying algorithm. All I've said is I'm going to give you a movie, and that movie, which is really large, should produce a very small value. So think of it as, super large movie, dot, 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 and it gets like funneled into a tiny or much smaller sequence of bits, but a sequence of bits that is in fact pretty secure, right? And there is like research in this area of integrity and hash values, and it is possible with a very, very low probability that some other movie could produce a hash value that is the same as this one. These are usually called collisions, but it's not something that, it's more at the research stage. So it's possible, but it's a very low possibility. Okay. All right. So now let's take a look at a simple hash algorithm. And this might look complicated, but you'll see it's actually quite simple. Once again, we're going to go back to XOR, which is, the underlying algorithm. And I don't know if I've mentioned this, I think I did, but why do we use XOR? Because what do we have in computers? We have circuits, right? We have circuits, we convert, we have like what are called logic gates, right? So you guys studied that. And so essentially we have circuits that just take, sequences of zeros, ones, 0, 1, and then you apply some kind of a circuit that does XORing. So it does that pretty fast, right? So that's essentially why we use this operation all the time. All right. So these are usually written like C, C++, OpenSSL is, but we're just going to use Python for most of our example. All right. So let's now take a look at what is called a simple hash function. So we're going to define it. And then at some point, we can start writing the code for it, and you'll see. So let's call this a very simple hash function. Very simple hash function. So practically all algorithms for computing the hash code of a message will view the message as a sequence of n-bit blocks. So we're back to that whole n-bit blocks, right? So the first step is we're going to have a message of size m, right? Of m that is of a specific size, and we're going to break this up into blocks of n bits, right? And so we're just going to say n bits block. And that's something that you define beforehand. So that can be 128 bits, 256 bits. The idea is, well, if you use a block that is 498 or whatever, that might take longer to encrypt, right? Because of the size. So it's going to slow down your internet, your computer. So there's a trade-off as usual, as I've said many times with cryptography. So more, larger blocks, larger keys might provide more security, but they also slow down the process. So you have to find that sweet spot. So for us, 128, 256. We will do some one lab at least that is just focused on performance, and you guys will see the difference. But yeah, so practically speaking, so I know I named this one. So practically all algorithms for computing the hash code of a message view the message as a sequence of n bits. Okay. Number two, so the message is going to be processed one block at a time in an iterative fashion to produce an n-bit hash code. So that's essentially what's going to happen is you can think of it. So now we take a block. We're going to XOR it with something else, maybe the key, right? And that produces another block, right? And so this is the first block. So now what do? We take the second block, XOR it with this, that produces another block over here. And then we XOR that one with a new block. And that's it. So that in the end, we have a block of size n bits that is essentially the hash value. Do you guys see that? So that is, a very simple hashing algorithm. You should be convinced that this actually meets the requirements, right? So you take a message, in a bit form, you break it into blocks. So you're taking something of variable length that is much larger, and you're converting it into something that is smaller, the size of n-bit blocks. You see that? So we go from large to small. Any questions? Yeah, go ahead. It's a little bit similar, but here we don't save this one to be sent. Instead, all we want is that one at the end. That's the difference, essentially. Good question. Any other question? All right. So yeah, so that's the idea. So we'll implement this, of course. Several of these we have to implement, but the message is processed one block at a time in an iterative fashion to produce a final n-bit hash code. Okay, you can see it's kind of the same ideas for all of them. So this is called, this is the simplest hash function. So you start with the first n-bit block, you XOR it bit by bit with the second block, XORing the result with the next n-bit block, and so on. And we can refer to this if you want. We can call it the XOR hash algorithm. So we can call this one the XOR hash algorithm. So right now, if I give you the function to take a string or whatever it is into a byte array, that's pretty much all you need to implement this algorithm. After that, it just becomes a trick of breaking the message into the blocks, performing the XOR, storing that output, and using it for the next, and so on. And you can see a lot of these algorithms then have kind of similar logic. All right. All right, so since it's lecture today, I'm just gonna lecture through some topics, and then once I finish this, we can start working on the assignment. So I'm gonna save the OpenSSL probably for Thursday, and today, if anything, if we start something, it'll be the XOR algorithm. Okay, so I have to give you the XOR one. That's just like the basic operation. We're just gonna see how it works. Then it makes sense to build this one, right? XOR hash. And then later on as we move on, kind of what your observation, right? You're saying like this is similar to the CBC. So yeah, exactly. So we're going to build the XOR hash and then you'll just tweak it a little and boom, now it's a CBC or an ECB, because essentially you were just saving the block. So you can see how nice this is, that it might amaze you that DES is based on this. AES is based on this. But the algorithms just have like more complexity, almost like human complexity. You know what I mean? Like XOR is elegant, is like what computers would do, what AI might do. And then DES and AES are like what humans do. You know what I mean? So it'd be interesting to see an algorithm created by AI for cryptography, right? So another XOR type thing that's different. That, be pretty neat to see. All right, but you'll see it. It's funny because it's just like adding, there's one part where you just take a thing, expand it, contract it, shift some bits over here. So that's essentially certain parts of this. But it's also very interesting. All right, so let's go ahead now. So we talked about integrity and we talked about the XOR. We're gonna go back now to symmetric encryption. So that means I'm going back to what? Confidentiality, right? So I'm gonna go back to confidentiality. I'm gonna go back to symmetric ciphers, and I'm gonna talk about one of the ciphers called the stream cipher. Okay, so this is another concept that we want to understand, which nicely actually ties into our first idea, the one-time pad or the OTP, right? So all of you should understand that by now, right? Because it's, I may ask questions about that, but this is, we had some problems with the OTP. So now we're going to look at the stream cipher to see if we can improve it. All right, so let's call this topic the stream cipher. Stream cipher. And I do have, I believe, a Python script for this one as well. So this goes back to the topics of, so we're going to go back to, we're going to go back to confidentiality. All right, so again, I want to scramble my data so people can't read it. So that's the stream cipher. I'm also going to go back to symmetric encryption. So that's kind of, whenever I'm doing these XOR operations, you can think of it that way. All right, so stream ciphers, right? So the stream cipher. So kind of the idea that motivates this, you might ask, like, what's the motivation of a stream cipher? Why does it even, is it just random that it exists? No, it actually has a motivation that smart people actually, came up with this. So they were like, well, Claude Shannon said that the one-time pad is secure, right? And why? Well, because it's random, but there's a few problems, right? One, we can XOR, but the problem is what? For it to be secure, the one-time pad needs what? Yes.
To be as large as the original data?
As the message, exactly. Yeah, exactly. The one-time pad needs to be as long as the message, right? That was, what Claude Shannon concluded. So, he's saying, okay, the OTP is secure, most definitely, but, assume that's a rectangle, so that's M, and assume this is like a movie. So that's really long. And the definition is basically saying that we can XOR with a key, but the key needs to be as long as the message. So that didn't work, unfortunately, right? So then some people said, okay, we know that's secure. How do we make the one-time pad practical? Because that was the problem. It's not practical, right? So the question is, how do we make the one-time pad practical? So the idea is, in the stream cipher, is to replace this totally random key. So that this key that is as long as the message needs to be random, 100% random, right? for it to work. So that's the problem essentially, right? And also that it's really large. So how do we do this? Well, the stream cipher tells you that you can replace the totally random key with a pseudo-random key. Okay, so that's essentially the idea. This in the stream cipher, we replace the rand, and this is pretty important actually. These things, like whenever you're thinking about randomness and things like that, it's completely different from like patterns. So it's funny, like language, right? I gave you the example of language. Language, NSE, very common terms. There's patterns there. Randomness, when you look at data that is random, it's like the total opposite. It behaves differently. It's all counterintuitive, right? But anyway, so in the stream cipher, we replace the random key, which, should be very random, the random key with what we call a pseudo-random key. So that's pseudo-random key. So that means, this pseudo-random key is still a sequence of bits. So it's still going to be, zeros and ones, not a problem. But obviously what we need is, instead of having a way of producing a random key, now we need a way to produce a pseudo-random key. And it's pseudo because we're going to have to use an algorithm. And an algorithm is going to be deterministic, right? That's something you guys learn. Algorithms are deterministic, except that it's going to start with a key, right? And the key is the thing that will provide the randoms, okay? So that's essentially, so you can already in your mind think, okay, if I was able to XOR a message to produce a small thing, how do I reverse that, right? It sounds kind of, I have a block of bits and then start reversing that to produce a longer thing that matches the message length. So that's essentially what we're doing. So we're going to need then to produce this. So now we're going to have I'm going to abbreviate this as PRG, because these are called pseudo-random generators. It's like a very famous term. There's a lot of research that goes into developing these functions for them to be obviously secure, right? Stream ciphers have been implemented. Like you might have had in the past maybe a Wi-Fi device or something like that, and it was using stream ciphers based on a pseudo-random generator. So it's something that has been used for those kinds of things, for confidentiality. So we're going to define PRG as a pseudo-random generator. A pseudo-random generator. Okay? So what is a pseudo-random generator? It's a function, right? Some code that we need to define. But let's give it a formal definition. So a PSG is a function, and we're going to denote it as G. It's a function G that takes a seed, and we're going to define that defined as I'm going to use this as a set from 0 to 1 of size S. So that's going to be the length. So S is the length of 0 or 1 bits. Okay, so S is the length. is the length of this sequence of bits. Let's say sequence. All right. So a pseudo-random generator is a function G that takes a seed defined as this, right? Defined as that. And the function once again, so the function G and the function G maps. So remember, this term maps just whatever you want it to be, but it'll take that input and convert it into another output. So the function G maps the seed to a much larger key. Larger key, where we define this key. So here you can see kind of the definition of this. So G takes 0, 1 of size S and maps it to 0, 1 of size N, where N is much bigger. So this means not just greater, but much greater than S. Okay, so that's essentially the idea. Why does it need to be much greater than S? Because obviously we're trying essentially to copy the one-time pad. And the one-time pad is for any message. Do you guys see the beauty of this? So it's kind of nice, right? So we had a problem with the one-time pad that we couldn't have a totally random string, but we don't actually, with this algorithm or this solution, need that whole key. We just need a shorter key, maybe 256 bits, but we have a function. And that function then will take that and just produce. And also, you don't have to produce the whole thing, right? Instead, you produce like every byte and you can send it out. And that's why it's called a stream cipher. So instead of producing the whole thing and sending it out, you produce one and then produce the next and produce the next and produce the next and produce the next, right? And so that's the essential key. But we'll see this in a little bit more detail. Any questions so far? All right, great. So as I said, where N must be larger than S. Now, the generator G does have to be efficiently computable. The function G is deterministic and only the seed is random. Therefore, it's pseudo-random, right? So there's some randomness to it, but for this to work, we need to do this. Okay, so imagine here, I'm going to give you a little diagram of how G expands. So we have K, right? This is K essentially. And we're going to use a G function, the deterministic algorithm, and this is essentially going to extend the message or the key. And there's no limit. That's the nice thing about it is we can just continue as long as the message is, essentially, because this key is just the function G with the key K as an input. Okay, so the algorithm will generate this. So this is kind of like an expansion, if you will, of the key. Okay, to a larger size that matches exactly with the length of the message we are dealing with. So now this is message and this is the pseudo random key. Okay, and we can perform then XOR. However, we don't perform XOR all at once, let's say. Instead, imagine that we do it on a byte by byte basis. So what that means is, we send this message, send this byte of the pseudo-random key, we XOR both of these and send it out. That's why it's called a stream. Then we take the next one, we produce them in real time, right? We take that, XOR those two. Yeah, sorry, this should be an XOR. And then we send that out. So we send it out in a stream. Think of it that way. Okay? So here we can just formally define the function. So we define the function of the pseudo-random or the process. Actually, this is the definition of the stream cipher. So the stream cipher can be defined formally as C. So this is going to be encryption of K and M, which this just means defined as. So it's going to be defined as M XOR the pseudo-random function with the key. Okay? So that's essentially the definition of it. So we take whatever the message is of any length and XOR it with the pseudo-random key. And that produces the cipher. The decryption can be formally defined as KC, right? So we have now the cipher and the key. And this is going to be defined as the cipher XOR of, once again, GK. So this means that Bob and Alice have to have the key, and Bob and Alice have to have the same algorithm, right? So that it's producing the same bytes. As a byte goes out, right? You run the algorithm from Bob's side, and then on Alice's side, you actually run the algorithm again to do the decryption, essentially. Right? So they have to be aligned. So a type of an example that's familiar to you of pseudo-random key is actually something that you use every day, right? When you log into the computer networks here, you use a key. I use a key fob, right? And you guys, I'm sure, have your iPhone or something like that, and it generates that little token, right? And magically, then it generates another token, and when you type it, it works for a little bit, right? That's exactly what's happening. Think of it that way, right? So you have that algorithm, you have the key. So a key was assigned to you, right? Everyone might have the same algorithm, but all of you have a unique key, right? In your iPhone. That's something that they did, right? And so that key goes in, the algorithm generates a number. And then that when you send it over the internet, on the other end, that same algorithm, knowing it's you, because you're the one that's doing it, is going to generate that same number. They match, and you do the thing. So it's a similar process in terms of the algorithm itself on your phone and on a server somewhere in the cloud. Does that make sense, guys? So that's you use this technique, essentially, is what I'm saying. There it's being used differently, but it's the same idea. Okay? So I'm gonna give you this is like bonus points. You don't have to do it if you don't want to. It's kind of like a crack this or solve this. All right, so I'm gonna give you a little idea. You have until the end of the semester. If you crack this, I'll give you bonus points. Okay? Makes sense? It's individual work. And you can just do research with it, and it's not so hard. All right, but it's just something fun to do if you'd like. All right, so I'm going to give this to you guys. And then you can ask questions if you have, or if you have questions now. All right, but obviously a lot of what we're going to be doing this semester is like understanding how things can be broken, what's the security of it, etc. So let's imagine this is related to the stream cipher. So I've given you the notation and I'm gonna write the problem in the notation, right? So you just have to think about it and then, give me like a conclusion at some point before the end of the semester so I can give you the points. So I'll ask the question. So this, I'll give you some context so that you remember. So this is PRG. So should I call this like what? Like it's not a quiz. This is like bonus. Let's call it bonus points. Bonus. I'm not gonna create a drop down, a Dropbox or anything like that. An assignment link, unless somebody comes in and says, "Hey, I did it." Then I will create one, and I can put the points there. Okay. So it's if you want to do it. So bonus points. So the context of this problem. So bonus points problem maybe. Bonus, whenever I say bonus points, it means you're not required to do it. It's just extra points that you can have. Remember, this is related to the pseudo-random generator, PRG. So this is in that context. And this is also a stream cipher. Okay, so here's the question. If you have two ciphers, generated with the same key, with the same key, so the same key K. Okay. So if you have two ciphers generated with the same key, can you break the cipher? Any of the ciphers. Or even, we can simplify to say this, can you make this more insecure or less secure? All right. But can you break any of the ciphers? So I'll give you some notation or some hint. So I'm going to say hint. Okay. And you guys can explore here. Again, this is pure research on your part, but I'm going to give you a hint. Say we have C1 and C1 takes M1 and then you XOR it with PRG of K. Okay, so you have that. So then you have C2. This is another cipher produced by another plain text message M2, and you XOR with PRG of K, right? So you by now should understand this notation, right? So there's a key. PRG is the pseudo-random generator, a function. You're XORing, you have message one, message two, and it produces C1 and C2. So I'll write over here. So C1, as this is just hints, C1 XOR C2 related to M1 XOR M2. And can this be broken? All right. So this is your hint. This is the research that you want to try. So if you have two ciphers generated with the same key, okay, so that implies you have C1 and C2, correct? And they were in fact generated with the same key, correct? So that's it. So if you have two ciphers generated with the same key, can the cipher be broken? So I've noted it, the hint, C1 comes from M1 XOR PRGK, C2 comes from M2 XOR PRGK. And so things that you can try or play with or research, well, you do have C1 and C2. So what happens if you XOR C1 with C2? Because you have them, right? You were able to intercept them. Why are you able to intercept C1 and C2? Because that's actually what's going in the wire, right? So when you tap that wire, you get that C1 and C2 and possibly more, right? So the vulnerability here is implying that they use the same key. And that's like the bad part, right? So play with this. So C1, C2, and how would that be related to M1 XOR M2? Now, you wouldn't have M1 XOR M2, right? Potentially, right? You would only have C1 and C2, and you would want to figure out PRG, right? And obviously with the objective of getting M1 and M2. M1 and M2 is the plain text message. Does this make sense, guys? So this is as I said, a fun hint scavenger hunt. See if you can find the vulnerability. Obviously, if you submit an assignment for this 1-2 pages, but you need to explain, prove, maybe with Python or with math or something, how this actually breaks. With an example would be great. All right. All right. So anyway, that's just like, bonus points problems. I'll do some of these throughout the semester or the scavenger hunt, things like that, for you to, if you're bored on a Saturday night, take a crack at this. Don't ask ChatGPT to solve it for you. Just can help you, but what's the point then? All right. Any questions? All right. So yeah, so we did one of these. Okay. And it'll appear on the on the README at some point. So, but this is mostly correct. All right. So now let's keep going. And let's see what else we have. I think it's like 5:02. So we have about 40 minutes. Yeah, so we have to start coding. All right. So I'm trying to think if I should start the XOR or if I have more. Yeah, the next set of topics is the block cipher. Block cipher. And I don't want to get into this. Oh yeah, that's right. So I remember now. All right, let's go through this. This is still a few more notes on the stream cipher. All right, and I think this is kind of the last of the lecture notes, and then we can probably start the XOR problem. So this is just a few additional comments on the stream cipher. I don't spend much time on the stream cipher during the semester, so this is pretty much it. And then we'll look at code examples and things like that. All right, so the stream cipher. Yeah, so the main processing step in a true stream cipher is the generation of a stream of pseudo-random bytes. Okay, and that's essentially the key, right? So what I was saying is you don't generate the whole block, right? The definition of it is that you generate a stream of pseudo-random bytes so that you're going to do the XORing one byte at a time. So whereas before we had blocks and we would XOR the whole block, now we have bytes. And so a byte of the plain text message and a byte of the pseudo-random key, and that those two get XORed and processed. So the stream cipher produces a stream of pseudo-random bytes. a stream of pseudo-random bytes. Pseudo-random bytes. And like I said, so the contrast here is you have some, function, and the function does not produce like the whole thing, dot, dot, dot. But instead it just produces, so this is not what it produces. Instead, it just produces one byte, produces a stream of pseudo-random bytes. So this is one byte. And just sends it, and then it produces the next byte, and so on. So similar to, imagine your key fob, like press a button, a byte. Press the button again, another byte, every so often, and it's changing, right, based on the algorithm that you have in there. So that's essentially the idea. So as a new byte of plain text shows up for encryption, a new byte of pseudo-random stream also becomes available at the same time. And this happens on a continuous basis. Okay? So that's essentially the definition of this. So the encryption then, you should understand at this point, it's as simple as it can be. You just XOR the byte from the pseudo-random stream with the plain text byte to get the encrypted byte. Okay? So we have like a message. We have a message, and we just pop off one byte. This is plain text, right? So this produces the block M, one byte. And then here the PRG, pseudo-random generator with the key also produces one byte of the key, right? And then you XOR both of these, right, to produce the what was the term? To produce the encrypted byte. So this is going to be the encrypted byte. Byte of data, so 8 bits. And then you're going to call the other one, we want to call well, this is the plain text byte. And we have the pseudo-random byte, let's call it. So the pseudo-random. Okay, so that is essentially the idea. And keep in mind that you generate the same pseudo-random byte stream for both encryption and decryption, right? So they have to be consistent so that you encrypt it and then decrypt it. All right, so here's a little diagram form. This is also in the slides. You can find it there. But this is going to be the figure, essentially, for the algorithm here. Let me go to another page. So you have the pseudo-random byte generator. So I'm going to write byte. So pseudo-random byte generator, one byte at a time. You have a key, of course, remember, for the algorithm. And this is going to be Bob. So this is Bob. This is going to be Alice here. So we got Alice. And so now on the other end, we're going to have the exact same thing, the pseudo-random byte generator. And this, of course, same algorithm, and they have to have securely exchanged the key at some point, which is what provides the randomness. Just like when you went to get your key fob or your thing on your app, you went somewhere to get that key. All right, and then here we're going to have the plain text byte stream. So the plain text byte stream. So the plain text byte stream, and it's just going to be that byte with this byte, and they're going to get XORed. Okay. Once you XOR it, you send it over the insecure internet. So this is going to be the ciphertext byte stream. Byte stream. And then, of course, this comes in over here, and it gets XORed, that cipher stream, with that, that new pseudo-random byte generator to produce the plain text byte stream. Okay, so this is the encryption, and then this is the decryption. Remember, what's the pillar that we're trying to achieve here? What's the related pillar here? Which one? Yeah, so there's a pillar, right? Which one? Confidentiality, right? So that's what I'm trying to protect the secret message. So the pillar here is confidentiality. Okay. All right, so I think that's all the notes. Ciphers, I'm going to hold off on this one. All right, so the next thing we're going to do now, so this is kind of the lecture part, like the theory. So let me end this video here.